Professor Jack Brouwer, welcome to Finalist Pitch Day with Halliburton.
Thank you for having me. It's an honor to be here.
And you've studied so many great new technologies. Let's go through some of them to see what you think are the most promising for the future. And perhaps we could start with fuel cells.
I have been studying especially renewable and sustainable energy conversion technologies for the last 24 years here at UC Irvine. And fuel cells are one of the main topics that I've studied. These are electrochemical energy conversion devices that produce zero criteria pollutant emissions. This is super important for air quality and health, but they also have very high efficiency, even when they are designed to be small power plants. What they do is they take fuel and convert it directly to electricity and heat. So if you need power somewhere, you can install a fuel cell, and with zero criteria pollutant emissions, you can actually make power efficiently and also heat.
Now, give me some of the science behind how it works, and especially the new science that you've been able to push to make it more efficient.
All fuel cells have three main components. They have two electrodes that sandwich an electrolyte, and then they have flow channels into which fuel must go on one side and air on the other. And the fuel breaks down and gives up electrons. The air breaks down, consuming electrons, and an ion goes across, and electrons are forced through the external circuit. So this is an electrochemical device. The chemical reactions happen with electrons. Okay, so electrochemical reactions. And the kind of fuel cells that I've studied the most are solid oxide. They're made from ceramic materials. And these ceramic materials, when they operate at high temperatures, they have low electrochemical kinetic losses. Okay, so they end up having higher efficiencies. They also have, with high temperature, the ability to integrate that high temperature with thermal processes, like processing of a hydrocarbon fuel. And so if you start out with a hydrocarbon fuel, a solid oxide fuel cell will always have the highest efficiency.
Give me some examples of how it's in practical use right now, how somebody could deploy one of these.
Yes. As a matter of fact, there's a very large market for stationary solid oxide and other types of fuel cell power plants in California, in the Northeast, in Korea, and then also other countries in Asia, China, Japan, etc. So stationary power plants have been installed, more than a gigawatt around the world, for producing power, mostly for commercial establishments, but sometimes also for utilities at substations. So these are existing products that can produce electricity cheaper than the alternative, and to do so reliably, 24/7.
Let's talk about some related or other technologies. Let's start with electrolyzers. You've been working on those, right?
Yes. So electrolyzers are the corollary type of technology to fuel cells. Fuel cells take fuel in and make electricity and water. Mm-hmm. Electrolyzers take electricity and water in and make fuel, hydrogen. So they have similar electrochemical reactions that go in the opposite direction. So water is in both compartments. And when you push electrons into one electrode and suck them out of another electrode, you bubble off hydrogen in this compartment and you bubble off water in this compartment. Again, by two electrochemical half reactions, one producing hydrogen, one producing oxygen from the water. So what you can do is you can take renewable electricity, put it into these types of devices, electrolyzers, and you can make hydrogen and oxygen for later use to produce electricity, or you can even use the oxygen for industrial processes or for medical applications.
Well, let's go to the hydrogen.
Yeah.
What excites you about hydrogen as a fuel source right now?
Hydrogen has the chance to be made from sustainable primary energy resources like wind and solar power, ocean power, biomass and biogas resources, and yet exhibit some of the features we need for our energy conversion economy to be sustainable, but to be reliable and resilient. If you have a grid that is supported primarily by sun and wind power, our fossil natural gas system provides a balancing, continuous power feature that is needed. Okay, today that's how we do it. Well, what if we don't want to use natural gas for that? The alternative that you can use for massive amounts of storage and for reliable transmission and distribution in pipelines is hydrogen. So you can see hydrogen can offer features like fossil natural gas does today in a future that doesn't rely upon fossil. So hydrogen is similar to natural gas in that it can be moved in pipelines. It's similar to natural gas in that it can be stored in underground storage facilities for massive amounts of storage. And it's similar to a fuel that can be carried around, stored for very long periods of time, and because of separate power and energy scaling, which I want to talk about a little bit more later, it can enable cheap, massive storage.
Let's go through that value chain you just talked about. Let's unpack it. You say storage, transmission. Let's start with storage.
Hydrogen pipelines are very similar to those pipelines where we move natural gas around in. However, they have different requirements because hydrogen interacts with certain metals and can degrade those metals. And so you'd have to learn the very types of materials that you can use for hydrogen. There also are components in that system like regulators and compressors and things like this. Hydrogen-ready equipment like that would be very necessary for us to invest in the future. When it comes to hydrogen storage, there are lots of interesting innovations that would be wonderful. Today, when we use hydrogen in vehicles, the challenge is that it has low volumetric energy density. It has very high gravimetric energy density. That is, it's very lightweight, but it takes up a lot of volume. So we have to compress it to super high pressures on board the vehicle. If there was a more elegant way to store hydrogen on board a vehicle that would not require all of that compression energy, that would be quite a wonderful innovation.
Is that why we're not using hydrogen vehicles as much these days?
No, I think the key challenge there is hydrogen infrastructure for fueling. And that's another area of innovation that I think entrepreneurs could invest in. Fueling stations and the infrastructure for transmitting and distributing hydrogen. There's a lot of innovation that could be made in that space as well. Let me talk a little bit more about storage for the grid, because there's innovations that can be made there too, because we already know that underground salt caverns have proven hydrogen storage capabilities. But we don't know that depleted oil and gas fields, where we store most of our natural gas today, could be transformed into hydrogen storage facilities. We also may have purpose-built both gaseous storage and maybe even metal hydride storage or even liquid storage of hydrogen. And there's a whole bunch of innovations in that whole space where we could build new facilities that could store massive amounts of hydrogen in these various ways.
A moment ago, you said you wanted to drill down on some of the processes involved with hydrogen. So let me give you an opportunity to do that.
Sure. So one thing to think about is that if we go to a highly renewable electric grid, so this is an electric grid that uses primarily sun and wind power, which, by the way, are more equitably available throughout society in all nations of the world to various degrees, okay? Much more evenly distributed than are the fossil resources today. But they don't offer the feature of being available 24/7. So they must be complemented by some storage function. Okay, so you can't just invest in sun and wind power, which fortunately they have come down in cost tremendously as we've been investing in them. But you can't build a reliable and sustainable grid without the storage function. But let me talk to you about the storage function, because if you only want 50% wind and solar power, you probably can complement it very well with natural gas And you don't need to have the features of hydrogen or even battery energy storage for that matter. You can just use natural gas plus solar and wind, and it works out well. And you can even apply carbon capture to the natural gas and do that for a long time. But many jurisdictions are thinking about higher than 50% renewable power going in. And that's when you start to need battery energy storage, one of the electrochemical energy conversion devices and systems that I like to work on. And that battery energy storage can do very well to take the sun power in the middle of the day and to return it to the evening almost every day. So you can go up to higher levels than 50%. Maybe you can go to 70% then if you add battery energy storage to the highly renewable grid. When you start to want more than 70% or so, okay, then you start to need additional functions because in some seasons, there is more or less sun and wind power available. And sometimes the sun doesn't shine and the wind doesn't blow for periods of a week or two. When you start to have these kinds of very large periods of sun and wind power not being available, then what you need is something that can store a massive amount of electricity. And this is when the features of hydrogen fuel cells and electrolyzers shine. Because you can size the electrolyzer power to the excess solar amount or excess wind amount you might have on a daily basis. And you can size the fuel cell, on the other hand, for taking the hydrogen back and making electricity for the deficit amount of power that you demand at any given day or hour. These usually can be relatively small. So for example, in California, they're about 30 gigawatts each. But if you want to store 2 weeks of energy, then you need this massive storage tank, which you can size completely independently of the fuel cell and electrolyzer. And that massive facility could be underground storage like we do with natural gas today. And as a result, you can make that sort of energy system with separate power scaling for the fuel cell and electrolyzer and energy scaling for the tank much cheaper than a battery energy storage system for the same amount of energy. And this is because a battery has a fixed power and energy amount. So every time you need more power, you buy more batteries. Every time you need more energy, you buy more batteries, and you just keep buying batteries and batteries and batteries. This is a very fundamental difference between hydrogen and batteries, and as a result, we're going to need it in a highly renewable energy system.
Okay, you've just said that batteries, which would be the alternative approach, have a fixed power and energy capacity. Are there advances in battery technology that you think will push that and allow? I've been working with Elon Musk quite a bit and dealing with the power wall that he's building, and I watch how that's increasing very rapidly. What do you see as a battery technology alternative to your hydrogen storage?
Yeah. So first of all, there are traditional batteries that are improving all the time, just like Elon Musk's. If you bought a Tesla back in 2010, the batteries weren't as good as they are now. Okay. So the traditional lithium ion batteries are improving all the time, but they still will always have a crossover point where the separate power and energy scaling makes the hydrogen alternative cheaper. So traditional batteries are improving all the time, and they're purpose making some traditional batteries with higher energy to power ratios for the grid. Okay. Cars have a nice power and energy balance already. Okay. So if you want a car, electric car, they make good batteries for those already. But for the grid, you need a lot more energy and not as much power. So you have to start scaling up the energy amount per unit of power. But again, they always will come fixed with that. Now, there are novel kinds of batteries, which we call flow batteries, which also have the feature of separate power and energy scaling, because they have the electrolyte that is stored in the tank over here and the tank over here, and they only flow the electrolyte through the electrochemical conversion devices when it's needed, right? When you're charging or when you're discharging. When you have this flow battery, you have these chemicals that are stored in tanks. For the hydrogen energy storage technique, you just need water. You don't need these chemicals. So you consume water when you charge the hydrogen energy storage system, and you make water when you discharge the hydrogen energy storage system. So places that might be water constrained could prefer these flow batteries and traditional battery energy storage systems. But people are looking at new alternatives for electrolysis that can directly use seawater and briny water, and are looking at, let's say, reverse osmosis systems and everything that may be coupled with electrolysis and fuel cells to actually make even dirty, polluted water and seawater electrolysis work. Let me just mention a couple of other things, though, because another technology that has separate power and energy scaling to enable really high renewable use is pumped hydro. So if you're in Norway, you have a very nice resource for pumped hydro. And this can serve some of the same functions as hydrogen might, okay? Iceland has similar characteristics. Okay, so around the world, depending upon what you have at your disposal, you may want more or less batteries, more or less hydrogen to complement your renewables.
Other things we haven't mentioned, including the new forms of nuclear we're reading about.
Okay, nuclear is very interesting. It's interesting because of its public policy framework in which it is introduced, right? So in California, we still have a moratorium on building new nuclear, and many other places too, like Japan, have public resistance. I think nuclear also is poised to have some innovations with regard to these small modular reactors, SMR as they are called, which may be quite attractive in a lot of jurisdictions. I think also there may be an innovation in the more distant future when it comes to fusion. There's been quite a bit of investment in fusion lately, and fusion has the great benefit of not having the waste streams that must be managed for the fission reactors.
Do you see that there's been a real breakthrough in fusion, or is that just a step-by-step improvement?
So fusion is a very challenging reaction to contain. So containing that reaction in a magnetic field or containing it in some other way is the biggest challenge. But there have been innovations and there's been huge investments. And even at UC Irvine, technology that came from UC Irvine is being advanced by TAE right now, right? Tri-Alpha Energy, TAE. So I think that there could be some real big innovations and discoveries that are made, because there's also the tokamak facilities that are located around the world that are doing innovative research in the fusion space too. I do still think that even with, let's say dramatic innovations, it's still quite a futuristic technology today. Whereas using renewable electricity, complementing it with batteries and hydrogen and fuel cells, yeah, that we can do today.
A lot of our listeners and people, including myself, by the way, have been very involved in legacy energy industries, oil and gas, my family in Louisiana, et cetera. What do people from legacy industries like that have to offer for these new technologies?
The cool thing about hydrogen fuel cells and electrolyzers is that they involve all of the building trades, the plumbing trades, the electrical trades, and all of the unions, okay, and their core competencies, right? Because these are electrochemical energy conversion devices, so they require electricians and electrical workers. They use pumps and fans and blowers. They need mechanical people. They use pipes, and so they need plumbing and pipe fitters. And so these kinds of expertise and core competencies in the traditional energy conversion fields are directly applicable to the future that includes not just electricity, but also includes gaseous fuel, and includes pipes, and includes chemical reactors and the like, right? So it's really important that we would actually be able to transform and provide green careers in this space. And hydrogen is one of those vectors that enables that. And it's not just hydrogen, it's hydrogen derivatives too, because from the hydrogen, we can make things like methanol, we can make things like ammonia, and we can use these things in steel plants and cement plants. And we can use these derivatives in things like ships and traditional energy conversion technologies. Whereas you cannot make a ship travel across the Pacific with batteries, but you can with hydrogen or its derivative fuels. You see, so again, it has these features that make it behave like diesel that it will replace. I believe that there is a chance that the Gulf Coast will become far more famous for hydrogen than California, partly due to your known set of skills and capabilities, right? With the energy infrastructure and energy technologies, we should allow for a framework in which we convert continually from our current fossil-based technologies to those which can enable sun, wind, bioenergy, and complemented by hydrogen and its derivatives. And its derivatives can be just like our current gasoline, diesel infrastructure that we are using today.
What about very high energy applications like making steel, or for that matter, even flying airplanes?
That's where the features of hydrogen and its derivatives really shine, because you have the opportunity with hydrogen and its light weight to actually use it on board things like ships or aviation for displacing and replacing fossil fuels. Now, some hydrocarbon fuels are probably going to be required, especially in things like aviation, but you can make those things like DMM, DME, alternative fuels from renewable hydrogen and captured or biogenic CO2. So you can react the hydrogen with CO2 to make these hydrocarbon chemicals that might be the future aviation fuels that we use. Onboard ships, our analyses suggest that you could use hydrogen directly. It would take up a little more volume than diesel does, but it would be lighter weight than the diesel. And so you can actually simulate a ship that goes all the way across the Pacific that can make it there with zero emissions, hydrogen, and fuel cell technology. We also have difficult industries, right? Some industries like steel making require a feature like chemicals that can react with the iron ore to make it steel, right? So you gotta have a chemical that reacts with it. You can't electrify that operation. You need a chemical, and hydrogen could be that chemical in the future that makes steel out of iron ore. Similarly with, for example, cement manufacturing, right? It needs a chemical to react with the calcium carbonates to make calcium oxides. These kinds of things require the features of hydrogen. There are also things like ammonia or methanol that require the hydrogen as a chemical feedstock. So you can start to see very important industries and very important transportation applications on the heavy duty side that need something like hydrogen and its derivatives.
Now, tell me what regulatory changes you think need to be made for these innovations to keep progressing.
I'm very pleased that we have begun some of that with the federal investment. There's several aspects of it. One is that they have agreed to invest in regional hydrogen hubs. There's $8 billion that the US federal government has agreed to invest in regional hydrogen hubs. I hope one will be in California. These regional hydrogen hubs will invest in the infrastructure, the connective tissue that is required to lower the cost, because we already know how to make hydrogen relatively inexpensively. Relatively, I say, because it needs to be still cheaper yet. But we don't have infrastructure that will connect the place of production to the place of consumption like we already have in the natural gas system or in the electric system. This is why battery electric vehicle charging has been cheaper than hydrogen so far. It's mainly because the infrastructure already existed primarily. We can charge our battery electric vehicles at home, but hydrogen requires new infrastructure. And so these hubs will help with that.
Would the simplest way of doing that and allowing the market to push innovation would be simply to have a tax on carbon?
Yes, we would allow innovation. We would allow companies to meet the demand for the renewable fuels and the zero emissions fuels in this way. I forgot to mention there's a there's a federal tax credit, both an investment and production tax credit that was also recently established in the United States. And that's also going to make a big difference with regard to investment early on. Of course, we can't keep doing that. Eventually, it has to become cost effective. It has to become the lowest price option, because then corporations will invest the hundreds of billions, not just 8 billion, but hundreds of billions required to make that an economic value proposition.
You know, you teach your students. I'm going in this afternoon to teach mine at Tulane. What do you hear from your students, and what would you suggest that they be studying right now?
So I hear from my students that they want to do something that is impactful, that is important, that makes a difference in the world. I think you and I both also want that to be the case for even what we do today. And from my perspective, so many people have focused upon solutions that don't scale. Eventually, private industry has to be the main driver for its adoption. If you try to establish a program like we have here in California, right, where we've built, 40 fueling stations, and we have 10,000 hydrogen fuel cell vehicles, 10,000 out of a vehicle population that's approximately 40 million. That's a drop in the bucket. Same with electric vehicles so far, even though they're more widely adopted today. It's got to be a solution that scales, that everyone in the world can adopt, that if we can make it the cheapest solution, then it can be adopted in India and in China and in all these growing economies as also the most environmentally sensitive and cheapest solution.
Thank you very much, Professor Jack Brouwer, and it's great to have had you with us. Very inspiring.
Thank you very much. I appreciate the opportunity.